Our current model of the outer solar system is being fundamentally challenged. The evidence lies in a handful of tiny, frozen worlds beyond Neptune, whose orbits are aligned with a statistical clustering so significant it suggests a compelling gravitational influence. Something massive, dark, and undiscovered is out there, and its gravity is pulling the strings. The terminal cursor blinked, a solitary green heartbeat in the oppressive dark of the data visualization lab. Dr. Kenji Tanaka leaned forward, the monitor's glow carving his face from the shadows. He ran the search query for the third time, an act born not of hope, but of pure methodical compulsion. The result: a null return. Billions of kilometers of surveyed space, petabytes of meticulously gathered photons, and the answer was a defiant, echoing void. There was nothing there. He pushed his chair back, the sound of its casters a violent scrape against the silence. For months, this had been the answer. The data indicated a consistent and profound void from the outer reaches of the solar system, a placid and predictable frontier. Yet, the numbers that scrolled through his mind told a different story entirely, a narrative of gravitational perturbations influenced by an unseen celestial mass. He closed his eyes, and the blank screen was replaced by a far more vivid image, the elegant orbital diagrams from the paper that had started it all. The work of Batygin and Brown from Caltech provided a robust mathematical framework, a mathematical key that turned a lock no one knew was there. Their argument was built upon the strange behavior of a half-dozen celestial exiles, fragments of ice and rock flung far beyond the orbit of Neptune. Each Kuiper Belt object traced a lonely, elongated path around the Sun, taking millennia to complete a single journey. Individually, they were unremarkable. Collectively, their configuration was highly anomalous. Their orbits were inexplicably aligned, their closest approaches to the Sun all clustered in the same quadrant of the sky, as if corralled by an unseen shepherd. The odds of such an arrangement occurring by chance were infinitesimal, a statistical anomaly. It was like finding footprints in fresh snow without ever seeing the animal that made them. The data suggests a massive body may be influencing their paths. This was the ghost Tanaka hunted, a world 10 times the mass of Earth, a true giant of the solar system, lurking in the abyssal cold. A planet 9 whose gravitational signature was etched into the architecture of these distant orbits, yet whose physical form remained stubbornly invisible. The theory was a masterpiece of inference, a portrait of an unseen world painted with the brushstrokes of celestial mechanics. It was precise, it was predictive, and according to the telescope, it was a fantasy. He opened his eyes, the sterile blackness of the survey results flooding his vision again. Here was the conflict that kept him in the lab until 3 in the morning. The raw observational evidence, the bedrock of his entire discipline, was in direct, violent opposition to the clean, predictive power of gravitational physics. It was a contradiction of cosmic proportions, a chasm between a universe that could be beautifully modeled and a universe that refused to be seen. The emptiness wasn't just an absence of data, it felt like a refutation, a silent, cosmic rebuttal to his entire search. The server room was a different kind of darkness, one filled with the low, steady thrum of immense computational power and the chill of industrial-grade air conditioning. In here, the universe was not a void to be observed, but a set of initial conditions to be built. Dr. Kenji Tanaka navigated the aisles of humming black monoliths to the primary visualization terminal. The observational data was a dead end. It was time to retreat into the clean, predictable world of mathematics. He keyed in his credentials and loaded the final output from a simulation that had been running for 72 hours straight. On the massive wall-mounted screen, a cosmos ignited. It began as a chaotic swarm of 100,000 points of light, a digital proxy for the primordial disk of debris that would eventually form the Kuiper Belt. The known giants, Jupiter, Saturn, Uranus, and Neptune, appeared as massive gravitational anchors, their orbits clearing wide swaths through the particle cloud. He let the simulation run forward, a counter in the corner of the screen ticking through millions of years per second. The virtual solar system settled into a familiar, stable architecture. The distant swarm of particles remained a largely disordered haze, just as one would expect. Then, he initiated the critical variable. A single command line and a new object was introduced into the system. An unseen perturber, a digital ghost with the mass and orbital parameters proposed for Planet 9. It was a dark behemoth on a vast eccentric loop, its path cutting a shallow angle across the ecliptic plane. Tanaka leaned back, his breath held. Now the true test began. He accelerated the clock, and the screen became a blur of evolving light. Eons passed in minutes. Slowly, almost imperceptibly at first, the ghost planet's influence began to manifest. It was not a violent force, but a persistent gravitational tide acting over geological time. Individual particles representing each Kuiper Belt object were nudged, their orbits gradually warped by thousands of distant gravitational encounters. The simulation was a majestic, silent ballet. As Planet 9 swung out to the farthest point of its orbit, its gravity pulled the distant objects along with it. As it swung back in, it scattered those that came too close. A pattern began to emerge from the chaos. The disordered haze was being sculpted. He watched as the orbits of a distinct population of particles were tilted, lifted high out of the plane of the other planets. Their perihelia, their closest points to the Sun, began to cluster together, shepherded into an anti-aligned configuration, pointing away from the perihelion of Planet 9 itself. Tanaka felt a surge of intellectual clarity, a deep satisfaction that erased the frustration of the empty sky surveys. He was watching the theory of Batygin and Brown play out, not as a series of equations, but as a dynamic, evolving system. The very anomalies catalogued by the Outer Solar System Origin Survey, the improbable alignments that OSSOS had confirmed, were materializing before him in the simulation. They were not flukes. They were the inevitable consequence of this hidden world's existence. The planet's influence was exactly like detecting an invisible ship from the waves it leaves behind. You could not see the vessel, but its wake betrayed its size, its speed, and its direction. On the screen, the final state of the simulated Kuiper Belt was a near-perfect statistical match for the observed one. The model provided a specific mass and orbital path. It was a mathematically consistent solution. The face on his screen was familiar, framed by a bookshelf overflowing with astronomical journals. Dr. Aisha Sharma projected an aura of cool precision, even through the compressed resolution of a video call. Her presentation at the virtual colloquium had been the most anticipated of the session, and she began not with an attack, but with a simple, disarming question laid over a map of the heavens. The slide showed the celestial sphere, stippled with the locations of every known distant Kuiper Belt object. Then, a second slide overlaid the first with a series of colored polygons, representing the precise footprints of every major sky survey from the last 2 decades, including the influential Outer Solar System Origins Survey. Her point was immediate and visually arresting. The discovered objects weren't scattered randomly, they were clustered almost entirely within the search fields. "We have only ever looked for our keys under the lamppost," she stated, her voice calm and even. The clustering of perihelia that forms the entire basis for the Planet 9 hypothesis exists within a dataset that is, by its very nature, profoundly biased. Kenji felt a familiar knot tighten in his stomach. This was the argument. Not an assault on the elegant mathematics of his simulations, but a fundamental challenge to the data he fed into them. Dr. Sharma methodically demonstrated how the timing of the surveys, the regions of sky they could observe from their terrestrial locations, and their sensitivity to faint objects all conspired to create selection effects. It was entirely possible, she argued, that a population of objects with orbits pointing in every other direction existed, but we simply hadn't looked in the right places at the right times to find them. The pattern wasn't a clue, it was a mirage born of incomplete information. The colloquium's chat window, visible at the side of his screen, began to pulse with activity. Other participants chimed in, raising alternative explanations that the Planet 9 model had overshadowed. One prominent astrophysicist proposed that the gravitational influence wasn't from a single massive planet, but from the collective mass of a vast, extended disk of icy debris beyond the known Kuiper belt, a sort of second, more massive belt whose integrated gravity could gently nudge the orbits of the smaller bodies over billions of years. Another suggested self-gravity, that the known Kuiper belt itself, if more massive in the past, could have generated the structures they were now misinterpreting. The air in Kenji's office felt heavy. The internal logic of his N-body simulation felt a million miles away, a fragile digital dream colliding with the messy, complicated reality of observation. This was the crucible of science. An elegant theory was not enough. It had to survive the onslaught of reasonable doubt. When the moderator finally called on him during the Q&A, Kenji took a steadying breath. Dr. Sharma's point regarding observational bias is not only valid, it is the single most critical challenge to this hypothesis, he began, acknowledging the strength of her position. However, the original analysis by Batygin and Brown at Caltech was not naive to these effects. Their statistical case was built upon a careful debiasing of the available data. He explained the complex calculations used to determine the probability that the alignment was real, even after accounting for the survey footprints. While the biases are significant, he concluded, our models show that they are not sufficient to explain the full strength of the clustering. There is a residue of improbability that still demands an explanation. His defense was solid, grounded in the rigorous work of his predecessors, but he could feel the shift in the room's virtual atmosphere. The narrative was no longer a simple hunt for a missing planet. It had become a far more complex debate about the very nature of their evidence. The session ended without resolution, the screen going dark and leaving Kenji alone once more with the silence. The echo of doubt, now louder than ever. The colloquium had not been a defeat, it had been a focusing lens. The chorus of doubts, particularly Dr. Sharma's incisive critique of observational bias, had forced a necessary and rigorous pivot. Instead of trying to prove Planet 9 existed with a single lucky image, Dr. Kenji Tanaka's team would now prove where it had to be by meticulously demonstrating where it was not. The new strategy was one of cartography, of drawing boundaries on a map of possibilities. His brightest graduate student, Maya, stared at a projection displaying the orbital path cone, a vast, impossibly large swath of the southern sky representing the planet's most probable territory. The search area is still astronomical, she murmured, tracing a faint arc with her finger on the screen. Even with the best telescopes, we're looking at decades of observation time to cover this. We're not going to cover it, Kenji replied, stepping beside her. He pulled up a different data set on an adjacent monitor. It was a heat map of the entire sky, compiled from years of all-sky infrared surveys. To a casual observer, it was a static-filled image, but to an astronomer, it was a chronicle of absence. These surveys saw nothing, no anomalous, slow-moving point source. And that, he said with a thin smile, is the most useful piece of direct observational data we have. Maya frowned. The Null result? How does that help? Because Planet 9, for all its ghostly qualities, is not a supernatural object. It's a physical body. It has mass, and therefore it has retained some amount of primordial heat from its formation. It should glow, however faintly, in the infrared, he explained. He began overlaying constraints on the orbital cone. The infrared surveys have specific known sensitivities. They can't see an object of X temperature if it's farther away than distance Y. So we can start to rule things out. If Planet 9 were as massive as 20 Earths and at the closest edge of its predicted orbit, these surveys would have seen it. They didn't. So we can eliminate that entire parameter space. He typed a few commands, and a significant portion of the search area on Maya's screen turned a deep exclusionary red. He continued, describing how they could cross-reference the planet's potential mass, its albedo, its distance, and its internal temperature. With each new constraint, another slice of the search box vanished. The hunt was being transformed from a search for a needle in a haystack to a precise survey of the few places the needle could logically be. Finding this world isn't just about adding another name to the roster of planets, Kenji said, his voice lowering with intensity. It's like solving a puzzle with one missing piece larger than all the others. Its discovery would force us to fundamentally rewrite the history of the solar system. It would provide strong evidence of a violent, chaotic youth for our planetary family, just like the strange systems we see around other stars. A history of orbital migration that displaced a significant planetary mass into the outer reaches. Over the next week, they worked relentlessly, integrating every available constraint. The vast nebulous search field shrank, collapsing into a few well-defined strips of sky. The search parameters were becoming increasingly constrained. The work culminated not in the roar of a discovery announcement, but in the quiet, methodical prose of a telescope-time proposal. It was a document stripped of speculative fervor, built instead on a foundation of rigorous elimination. It asked for a specific number of nights on a specific telescope to look at a specific, narrowly defined coordinate range. On a Friday evening, with only the hum of the servers for company, Kenji attached the final PDF to an email addressed to the allocation committee of the Mauna Kea Observatory. He paused for a moment, his finger hovering over the mouse. This was not the end of the search. It was the end of the beginning. He clicked send, and the hunt for the phantom world took its next decisive step out of the realm of pure theory and into the focused gaze of the world's most powerful eyes. That gravitational signal from the edge of our solar system turns out not to be a single clear cry, but a faint and complex echo. Answering it requires more than just powerful telescopes. It demands fierce debate, intellectual resilience, and the courage to redraw the very map we thought we knew. This is the quiet, essential nature of discovery, a process of relentless refinement, forever chasing the ghost in the machine. This journey through theory, doubt, and progress is exactly what we love to explore here at TECH DISSECT Official. We're curious to hear your thoughts in the comments. In the face of such powerful mathematical models, do you believe Dr. Sharma's rigorous skepticism was more crucial to the scientific process than Dr. Tanaka's persistent faith in the theory? Thank you for joining us on this journey to the edge of our cosmic backyard. We'll see you again soon, but until then, consider this. What if the gravitational whispers from the dark aren't a single planet at all, but the collective ghost of a trillion unseen objects?